Alright, so let's go over these. As you can see, the first part of this is, here's a bunch of reactions, predict the products of them. And these are very much like questions you'll see on an exam. Every exam going forward is going to have a page, or sometimes even more than that, of questions just like this. Here's a bunch of reactions, tell me what the product is. What becomes important in these cases is to know what the reagent is and know what functional groups it's going to react with. Then find those functional groups in your starting material and actually do the reaction. So right now, that one of those parts is pretty easy. We've only learned reactions of alkenes. And this molecule we notice has two of them. And so the HBr could react with either of the alkenes. And so you could give an answer where it reacted with this one, put the bromine there, or where it put it over here, or both. Just remembering that HBr addition is a Markovnikov process, and so the bromine ends up on the more substituted carbon and the hydrogen on the less substituted. Our second reaction is the oxymercuration, which we know reacts with alkenes to form alcohols. And again, specifically, this is a Markovnikov process. So it gives us the alcohol on the more substituted carbon. Also important to keep in mind is that the alcohol reacts only with the alkene, and that aromatic rings are not alkenes. And so the aromatic ring stays intact. Part C is our hydroboration reaction. That gives us an alcohol also, but unlike the oxymercuration, is an anti-Markovnikov process and gives us the alcohol on the less substituted carbon. Part D is the Simmons-Smith reaction. That forms a cyclopropane ring from one of the alkenes. Part E, we have a hydrogenation, but there are no alkenes in this starting material. The starting material is benzene, which is just an aromatic ring. So what will happen here? Nothing at all. F is the epoxidation. Again, you could do it on one alkene or the other. I'm just going to choose to do the alkene that's outside of the ring. But again, you could have done the alkene over here, or you could have shown both of them as epoxides. G is also a hydration reaction. This is the acid catalyzed hydration, also a Markovnikov process. And then part H here looks kind of like a hydroboration, but if you look carefully at it, that's not the correct reagent for a hydroboration. Hydroboration requires BH3. Since we don't have the correct reagents, it's not going to do anything. Part I, we have our Simmons-Smith again, so we'll form a cyclopropane ring from the alkene. Part J is the bromination, but there's no alkenes, so nothing will happen. Part K is also a halogenation or bromination, but this time we do have, in fact, two alkenes, so either one of those can react. And the last of these, part L, is a hydroboration, and as we know, hydroboration gives us the alcohol at the less substituted carbon. All right, in question 2, we are determining mechanisms for the reactions. So first we have our acid catalyzed hydration. So we know that the alkene will attack the acid. Gives us the more substituted carbocation. Water is able to attack that. And then we lose a hydrogen to get to the product. Part B is the Halohydrin Formation, which is the halogenation in the presence of water. So our alkene attacks Br2. That gives us our bromonium ion. The water then attacks at the more substituted carbon of that three-membered ring, opens up the three-membered ring, which gives us this intermediate, which can then lose a proton to get to our product. Alright, our remaining questions are ones that ask us to look at some more unusual situations with alkenes. So, question 3 here, we have a reaction and we have two possible products that form. And we want a mechanism that accounts for both of them. So the product on the left looks exactly like what we would expect to see from a halogenation. We get the three-membered bromonium ion, which then gets opened up by Br- to form the product. But where does the other one come from? Well, once we have this other alkene nearby, we can have this slightly unusual step where that alkene adds its electrons in, and that forces the bromonium ion to open up. And then the Br- attacks down here at the bottom, and that gives us the product on the right. So anytime we've got an alkene near something that's positively charged, different or unusual things are capable of happening. All right, question 4 says if we have propene and we add HCl and do this in ethanol, the product that we get is this one. It's not the hydration product. And how do we get that? So if the alkene attacks the HCl, we form the secondary carbocation. Normally in this reaction we then get water to attack and form an alcohol. But if we have an alcohol here, ethanol, that's present, that can function as the nucleophile instead, and after it loses a hydrogen, it's going to give us an ether as the product. Question 5 says we have propene, ethene, and 2-methylpropene. And the question tells us that they react at different rates. And we want to know which one's going to react fastest, which one's going to react slowest, and why? Now, in each case, if these react with HBr, let's draw the intermediate. And from here, we can probably see the difference. Propene leads us to a secondary cation. Ethene gives us a primary cation, and 2-methylpropene gives us a tertiary cation. Now we know the tertiary cation is the most stable, and that means that it's going to form most easily. Whereas the primary cation, being the least stable, is going to be the hardest to form and will form slowest, and propene itself will be in the middle. All right, question 6. We're saying that both carbons of our alkene are secondary, but which one's going to be favored? Well, if we look at the carbocations that form, they're both secondary. But the one on the left, that carbocation, is stabilized by the resonance from the aromatic ring. The one over here on the right is too far away from the aromatic ring to get any resonance stabilization. So it's less stable, it's not going to form as easily. The one on the left is much more stable, and so that's the carbocation that will form and lead to the product that we have drawn. And question 7 is really something we've already talked about in class, but we'll go over it quickly. If we try our oxymercuration reaction, but we have an alcohol present instead of water, we've seen previously that the water or the ethanol or whatever alcohol is present will attack instead. And so instead of getting the alcohol as a product, ultimately what we end up with is an ether.